So our first keynote speaker today, Dr. Alexander Kott, is the chief scientist of the United States Army Research Laboratory, where he leads the development of the lab's technical strategy. He drives the quality of ARL research, and he represents ARL to the external technical and academic community, which is why we are lucky enough to have him here today. Dr. Kott has had a long and distinguished career in federal research at the cutting edge of research on machine learning, autonomous control, cyber defense, and network science. First as a DARPA program manager, then as chief of the Network Sciences Division at Army Research Laboratory, and now as ARL's chief scientist. Dr. Kott is the recipient of the Secretary of Defense Exceptional Public Service Award and the accompanying medal. He's published over 80 technical papers, developed, co-authored, and edited over 10 books. Also, on a personal note, Dr. Kott is actually the person who got me into this field with my first job out of my postdoc. So if you don't like my talk tomorrow, you can mostly blame me, but also him. So please join me in welcoming Dr. Kott to the stage as for his keynote, Bonware to the Rescue.
Thank you, Richard, and thank you everybody for having me here. I love this place. I love the vibe, the environment, the venue. Thank you very much for selecting such a wonderful venue. Is this the last year it was here as well? Yeah, a different location. Well, anyways, I usually don't get to present my talks in such exciting places. Usually it's a much more boring hotel conference room, and but I love it here. I also love this couch. If I get tired, So we at the Army Research Lab, we're focusing on foundational research for applications and systems that are of interest, that are valuable and critical to the United States Army, to warfare, to ground warfare. However, we do focus on foundational knowledge for building this kind of systems and weapons and applications. My talk is kind of both applied in terms of focusing on needs more than how exactly to accomplish those needs, as well as somewhat futuristic, because it's our job to focus on the future, look about somewhere between 10 to 30 years from now. So with that, let me transport you from this, clicker doesn't work. Maybe it, okay. How's that? Let me transport you with one click from this wonderful and warm and funny place to this dystopian world, this dark and dangerous and unpleasant world of destroyed cities where soldiers of competing nations are fighting each other. And the key point of this picture is that this world is saturated with intelligent things. Look at all those robots, aerial robots, ground robots that you see in this picture. There are many more invisible intelligent things and intelligent agents within this world. And humans, in fact, are probably going to be a lot less visible. If you look at the soldier who is very prominent on the foreground, this is more of an artistic license. That soldier probably will not want to be sticking out like this, because it is an invitation for not being alive extremely soon. This is the world of intelligent things. And the human beings are just a part of that world of intelligent things. So when I talk about, for example, the buzzword of Internet of Things, or as we call it at the Army Research Laboratory, Internet of Battle Things, I think it's a misnomer. It's a misnomer in the sense that we need to get used to something radical. We need to get used to the fact that in a world of near future, we, human beings, will be merely one of the species of intelligent beings. The humans will be just merely one of the species of intelligent beings. If this sounds radical, that's because it is, and we will have to get used to it, and we will get used to it, because it's coming, and it will be reality within next easily 20 years. This is a challenging notion because we humans don't coexist very well even with members of our own species. We find ways to fight each other very bitterly. Imagine how we're going to coexist with variety of species of intelligent beings that we will be seeing both in a kind of a warfare world as well as entirely civilian and consumer world. The intelligent beings will be of all kinds of types. They will have very different nature. They will have very different capabilities and interests and roles and intentions of their own to some extent. Look at all the varieties here. There will be intelligent munitions. There are already intelligent munitions on the battlefield. There will be, of course, intelligent sensors. There are already some intelligent sensors on the battlefield. And robots, of course, and wearable devices, and weapons. And, of course, the autonomous vehicles. And, of course, endless number of autonomous agents of purely virtual type. And it will be, I keep forgetting that this clicker doesn't work. Of course, we humans will have to not only coexist with them, we have to team with them. We have to become their brethren in arms, if you wish. We have to work with them, we have to fight with them, we have to become their buddies. We have to be able to explain to them what we mean and what we want. And it's not just simple commands, it is actually a conversation about complex tasks, about complex missions, about a lot of uncertainties and dangers and confusion and so on. And in addition, of course, they will have to be able to tell us what's going on, what do they see, what do they think about it, how do they interpret it. This is a realistic world that is coming upon us already, and much more so within a few years. So, of course, one of the problems with this world is that it is a world of high vulnerability to cyber threats. The more intelligence we put into the world to work with us, the more vulnerabilities, the more opportunities for the enemy to invade that world we are creating. And so I would say that the artificial intelligence and machine learning is a triple-edged sword, intelligent beings, artificial intelligent beings, are targets of cyber attacks. They are also perpetrators of cyber attacks. And the third edge of that sword is they're defenders against those attacks. And I would argue that in this world, the humans are probably the least effective defenders. Everything happens much too fast, with much too complexity. And my argument is that human-based cyber defense is going to disappear, or at least become very different from what it is today. The bulk of the work of cyber defense will have to be taken by intelligent entities themselves or intelligent agents that reside on those autonomous entities. And I call those cyber defense agents, these autonomous intelligent agents, I call them Bonware. We all know about malware, but let's try to imagine what a bonware, a goodware, might look like. Why do we need bonware? Because humans are going to be the weakest links. They are the weakest links in the cyber world. They will be even more so as the years come by. The humans will be continuing to participate, of course, in that, but at a higher level of abstraction, on higher level of decisions, at a higher level of comprehension of situation. The bulk of the work will have to be done by artificial intelligent autonomous cyber defense agents. And so let me tell you a little bit about some of the work we're trying to do to envision how those agents might look like. A couple years ago, I created a NATO research group on autonomous, intelligent autonomous cyber defense agents. And our objective was to create a preliminary, how should I say it, a sketch of what an agent like this might look like. What might be what we call a reference architecture of that agent, what might be some of the directions towards implementing such an agent, and so on. So let me talk about this a little bit. In fact, I see a couple faces here in the audience who actually were engaged in some ways in that activity. So again, this is a NATO activity. I don't know if anybody of you ever participated in any NATO research groups. Please raise your hands. I don't expect any hands. Oh, whoa, whoa, I see two, great. This one is entirely open. It is public releasable. You can join it. In fact, I would urge you to join it if you think that this is relevant to your work, to your research, to your products of your company. We made the following assumptions about the context in which we envision that agent operating. This agent will be residing on some kind of an autonomous entity, such as an autonomous vehicle. It could be a combat vehicle, it could be a logistics vehicle, it could be intelligence gathering vehicle. There could be multiple, of course, computers on that vehicle. In fact, most of autonomous vehicles have multiple CPUs doing different things. Therefore, there could be multiple agents residing maybe in individual elements of that computing system or in a more centralized way. But most importantly, there are two things about it, three things. First, decentralized cyber defense will be impossible in that environment. Why? Because communications will be very difficult and very dangerous. Therefore, sending data from a particular computer to some centralized node for analysis and detection of intrusion and taking appropriate actions will be impossible. It will be too dangerous. It will be simply impossible because the enemy will interfere very drastically with communications. Secondly, there will be no human being on that vehicle to take care of any alerts that you might be sending to a human being. That human being is way too busy. If it's a fully autonomous, uninhabited vehicle, then of course there is no human being there. But even if it's a tank with several human beings inside of it, these people are way too busy fighting the war or doing other things to take care of alerts or being system administrators and so on. Furthermore, majority of our wonderful soldiers are, very young. They have high school education. They don't necessarily have any exposure to cyber education. Even if they have some, it's probably not going to be adequate to deal with a complex attack that is likely to be perpetrated by a serious enemy. So, no humans, cannot rely on humans. You have to do it autonomously. And the third interesting fact is that the cyber defense agent will have to be stealthy. It has to be hiding, because the first thing that malware on that computer will try to do is to find that agent and kill that agent, right? Therefore, it has to make itself as invisible as possible. That means, among other things, that any action or observation that it makes has to be hidden. It has to be as few of them as possible and as hidden as possible. So read as little data as possible. Because any reading, any access to read the data will be noticed by the malware. Bonware have to survive while being constantly watched by the malware. So, nevertheless, that agent will have to find that malware and will have to take decisive actions to actually degrade or defeat that malware. I already talked about very limited opportunities for human control. The agent may try to ask the human operator of some sort, hey, should I delete that application, or should I shut down that particular channel of communications, because it is going to have some unpleasant ramifications for that system. But it may not have the luxury of doing this, so it will have to make those hard decisions on its own. And therefore, it will have to accept the risk, and that means we, the owners of that Bonware, will have to accept the risk. Now, that's where we start to see a serious difference between the military world and the civilian world. The risk that may be perfectly acceptable in the military world may not be acceptable in a consumer world. Because the alternative to not taking an action by an autonomous agent might be a destruction of the entire vehicle or humans involved in that fight by the adversary. Now, on the other hand, the stakes are not as high in civilian world, so where the risks are exactly is not entirely clear to me. This is an interesting conversation for ethicists, for lawyers, and ultimately it will be an empirical decision as to what works, what doesn't. So it's really you that will decide what works and what doesn't. So I already talked about some other requirements. We published a reference architecture already, and it's an early version. It's easy to criticize, but it at least gives a flavor of what we're thinking about, and we're hoping to release in a year or so a more comprehensive reference architecture. And if you would like to participate in that, we would love to have your participation. If we're hoping to actually have references there to existing products, existing companies that reflect some elements of those capabilities. So if you want to be on that good list that will be distributed to all the acquisition officials within the NATO countries, then your company may be quite interested in doing that. So I will skip some of some of the elements within that architecture. We talk there about how to perform planning of activities, how to perform appropriate action, select and perform appropriate actions, how to collaborate and negotiate if the agent has the luxury of collaborating and negotiating with another agent. Remember, communications are very dangerous, therefore any collaboration is actually dangerous. So there will be a limited amount. Will be very frugal collaboration. And of course, there is a tremendous opportunities and need here for learning. This autonomous intelligent agent needs to learn, because the tactics and techniques of the adversary will be changing very rapidly. We cannot simply install that agent on a tank, for example, and expect that it will be effective for some number of days or even hours, because things will be changing rapidly. New constant flood of new approaches and techniques will be probably experienced by that agent. So it has to learn. It has to learn at least that certain things that used to work no longer work, and he has to try something else. So what kind of things could be learned? The world dynamics is certainly one of the things that can be learned relatively straightforwardly. In other words, what kind of actions lead to what kind of changes within the system, how the state changes from one state to another given a particular action, rewards for action, a sequence of actions, and of course, perhaps meaning interpretation of various sequences of activities, observations. So one approach, perhaps the most straightforward, is the good old or bad old, depending on your perspective, case-based reasoning, which even in my days of early 80s, of applied AI in early 80s, that's, yeah, I'm that old. Even then, it was a kind of a well-known technique with its all well-known benefits and its very well-known deficiencies and challenges. Nevertheless, there's no reason not to try something like that because it can be implemented relatively easily. By the way, I haven't seen a lot of interesting work in the intersection of really serious case-based reasoning and machine learning, modern machine learning. If you see something like that, point me to it, because this might be an interesting iteration on the case-based reasoning. But anyways, the simplest point is if you have many cases for which you have sequences of actions, sequences of observations, and some measure of goodness of the state, then you, given any current set of observations and actions, you can say, well, can I match it to some of the previous cases? And if I can find the ones that seem to be good, that means that's the action or sequence of actions I should be taking in the near future. So it's pretty straightforward. Of course, the devil is in implementation, which becomes very difficult. Of course, we could try to learn through some sort of neural networks. Here's a very crude sketch of that. Given a sequence of observations and actions that recently happened, or if happened at some number of epochs previously, you can learn what are appropriate, most beneficial actions for the future. So that's perhaps another approach. Again, we're not trying in our reference architecture to give prescriptions for solutions. We're trying to give some sketches of possible directions for thinking. So we actually have done a related project at the Army Research Laboratory where we developed an active defense agent with a particular focus on learning the model of the adversary decision process, how the adversary decides to do actions depending on previous actions, depending on success of those previous actions, and so on. We're also trying to learn the rules for kind of a robust but simple rule-based decision-making on what to do next, how to stop the adversary from exfiltrating data or from continuing intrusion or propagation and so on. And we are focusing on kind of variation of deception. We're not trying to stop the intrusion or eliminate the malware. Rather, we are trying to make the adversary to think that he is kind of succeeding, but leading him towards very slow results and least profitable results to the adversary. And we, in fact, happen to have an implementation of that. We have a prototype. It shows some reasonable results, at least for a small set of examples. What else can I tell you? Another very desirable application of machine learning is in modeling the effects. Look at this agent. It needs to do something. It needs to do something active. Well, actions have ramifications. Some of them are positive, some of them are negative, some of them are immediate, some of them are propagating a little later. Currently, there's very few tools for actually modeling these effects. What happens in the interactions between the attacker and defender, and what happens as a result of their actions. The best example I know in this area is the prototype built by MITRE. It's called Amica, and they're actually building there a fairly rigorous model of how the attacker behaves and how the defender behaves, and the structure and behavior of the system itself that is being defended. And it actually works reasonably well. It actually shows a lot of promise, except for one thing. It is incredibly expensive to build those models. So you can't really afford to build them by hand as they did. They have to be built automatically somehow. And that's where, again, machine learning can play an amazingly important role. So here is another pointer to an important class of products. So let me skip some of the details about Amica. If you can easily find it online. There are some papers published. And finally, I would like to talk very briefly about an 800-pound gorilla in the room. And that 800-pound gorilla in the room is that AI has always been very promising, and AI always was facing a lot of skepticism for very good reasons. AI is the future, and it always will be. And the problem is that AI, in spite of wonderful successes of particularly the last 10 years, you know what you can do by taking an old concept of neural network and renaming it deep learning? Wonders happen. No, there are many other important reasons why good things have happened in the last 10 years or so. And in spite of all those successes, there are some very serious gaps. This is actually a good list. If you want, you can get it from me, a good list of gaps that we identified in how AI is limited, what are the gaps in AI applications to real-world complicated problems, such as that dystopian world that I showed you on the very first slide. For an AI to operate in that horrible, difficult, complicated, uncertain, and dangerous world, it's not ready. Here are the gaps that that it needs to be covered. I like to distill this to what I called D5. D5. So repeat after me. D5 stands for dinky, dirty, dynamic, deceptive data. Dinky, dirty, dynamic, deceptive data. Dinky is, of course, that you don't get millions of examples. You get a few examples if you're lucky. Dirty is that most of the data that you get has no relation to, no relevance to what you actually need to learn. It is noise, it's dirt. Dynamic is because everything is changing, as the enemy is, the adversary is always changing its tools, its techniques, and so on. And your own world is changing constantly. So anything you learned yesterday may not be applicable today, or at least you don't know if it's applicable. And deceptive is a terrible vulnerability of machine learning, and that is, of course, the infamous adversarial learning. We at the Army Research Laboratory are paying a lot of attention to this. We've done some good research in collaboration with academics, showing that it is incredibly easy to automatically generate deceptive inputs to a machine-learned algorithm that works very, very reliably, even without knowing anything about the specifics of that machine learning approach. All you need to know is to have some idea about the data that they used to learn it, and that is relatively easy to either obtain or to approximate in some ways. So the deception is extremely easy against machine learning algorithms, and we know that, and our adversaries know that, I assume. They read the papers, so they know. This is a huge problem. So the fourth D in that D5 is deceptive. And of course, the last one is data, which are always hard to collect, hard to maintain, hard to release, and so on. So let me just finish with saying really rapidly a few sentences about kind of work that we do at the Army Research Laboratory to overcome those gaps. One thing we're doing, we've done some pretty good research in adaptive real-time learning during performing a mission. In other words, during performing a certain task, you can actually observe the success or difficulties of performing it. You can learn that online, you can learn it in real time, and you can actually use that in real time as well. Of course, that throws that invalidates any verification and validation. It invalidates any certification. So this is, of course, a very challenging issue from that perspective. We've had some really good success in the last year with several techniques that help humans to direct machine learning process and dramatically speed it up. In many cases, it is almost impossible to get the machine learning algorithm to converge without some human input. And what we found is that there are some good ways to actually provide that input that helps to speed up learning dramatically, much faster. Here are some publications about that. Semantic concepts learning is very important, but it's clearly very futuristic. We had some successes. We recently had excellent results in using EEG to actually read the human mind. Remember, the intelligent agents actually need to understand what the humans are trying to do. So one way to do that is to read the human mind. EEG is not a bad way to do that, and you actually can put the electrodes into the helmet. In the battlefield, it is easy, maybe more difficult in the consumer world, though. And of course, a natural language interaction that goes beyond Siri and Alexa, beyond a single question, single answer, but rather goes into a dialogue, a real dialogue that actually takes into account the context, the meaning, the objectives, the intentions, and so on. We also do some work on cyber deception. I just talked to somebody in this audience about the importance of cyber deception. One of the most powerful tools that a cyber defense agent can use is cyber deception. It's better than just trying to block the malware. And there, of course, there is no science currently behind that. And so we are actually we have a fairly large program of developing a science of cyber deception. And with that, I will there's some reference you can read on most of the topics I mentioned. And the final word, we are very interested in working, collaborating with industry, academia, and industry. And so if anything of this sounds interesting, if any of this is relevant to what you would like to do, talk to us. Talk to us. You may find that we can, if not give you money, we can at least join the forces with you and thereby multiply our joint team beyond what you might be able to do yourself. We have a number of companies that collaborate with us on various projects of interest to them and to us, and it works quite well. And that's about it. You can ask me questions. I will go on the couch. Yeah.
Thank you, Alex. Several questions, but I'm going to focus on just one so that other people can ask. The last point you made about the science of adversary kind of thinking, decision-making models. Even if we can do it, and even there are people already doing it, how do you see that those models or the science of approaching to get to the models be shared across communities? The reason I ask that is that you can imagine that, oh, I got an adversary model, the way I know this is my secret, I don't want to let other people know. That's the typical thinking behind intelligence communities and industry as well. How do you see the sharing and not sharing about this science of adversary model?
Yeah, I think the answer is like with all other technical knowledge. Some of it is shared and some of it is kept proprietary. People share more abstract and more foundational knowledge. They share templates, they share representational paradigms, they share some knowledge about how those paradigms work or don't work. But when it comes to developing a particular model of a particular adversary for a particular customer, that typically is kept proprietary. So I don't think that will change in this case. It's pretty much the same as with most other forms of technical knowledge. Yes, sir. I will try to repeat your question if you speak loudly.
Could you elaborate a little bit on the human-in-the-loop interactions that you were talking about? I'm particularly interested in trying to use that to gain maybe weak labels or fuzzy labels to label data sets where it's very difficult to get sets to training.
Right. So, yeah, the human-in-the-loop learning. I'm not the best person to give you details. There are several fairly detailed papers that are published, and I can, in fact, connect you directly with the with the team that did that research, and they would love to talk to you because you're talking exactly about the challenges that they were facing and they were trying to overcome. Yeah. But Humanintheloop is a interesting approach. The only problem is that it goes against the grain of much of what I discussed about the autonomous agents that do not have an opportunity to interact with the humans because of the security concerns or lack of communication channels. So. Mm-hmm.
You mentioned the concept of agents having to do local learning and also limited communication because it's in an untrusted data environment. You can envision over time this might lead similar agents to take slightly different actions. Do you envision agents being coupled to hardware or perhaps agents being issued to the warfighters so that they have consistent behavior even if they are changing equipment?
I would envision that they will not be coupled to hardware. But they could be. I think this is really an implementational decision. They probably need to be updated rather frequently, even if there is an opportunity to bring that vehicle back to the base or somewhere where communications are possible and reliable and protected. Then that Bonware will be frequently updated, I would envision. Will they be all consistent? Not necessarily. Each one of those agents may have different experiences. So unless it's brought back to the base and resynchronized in some ways, they will in fact learn different behaviors, some of which will be better than others. Right here. I will repeat your question. I will try to repeat your question.
Second one,
that's right.
I think we were actually contemporaries at one point. I was solving similar problems in the UK. And we were looking at partial probabilistic networks, so looking at artificial creativity, because it is a creative problem. How do you adapt to new problems with old partial solutions? There was some work at George Mason University might be helpful too. More of a comment.
Right, and thank you for sharing. That's a very good point. That tree-based models are in fact kind of intersection of CBR and more classical machine learning. Yeah.
But also looking at probabilistic network models, which are
probabilistic networks. Yes. Thank you for sharing. Thank you. Mm-hmm.
Hi, can I?
Go ahead, please.
So you mentioned the D5 challenge, but where are the data sets? How do I create a data set with D5 properties? And I could create one, but how does that match? How do I know it actually has some general applicability? So do you have some data sets to share, or maybe have a challenge that?
Oh, you're asking whether we actually have some data sets to share. Actually, this is always a challenge because the data sets that we collect tend to be not very suitable for distribution. Nevertheless, I think we do have some, and I don't quite know where that. We had a program of developing data sets that we can share with academia. I need to check on where that stands. Please do contact me. Please get in touch with me, and I will put you in touch with those people who actually were trying to do that. There might be something that you will find interesting there. Yes, sir.
I'm very new to machine learning, so I was curious if you could explain the difference between case-based reasoning and the neural network.
We don't have time in this 2 days to do that, probably. But in the most, well, I'm sorry, probably not prepared to answer this question. Why don't we get together after this session, and then we will talk, okay? Yes, sir.
Just a question on your overall sketch of what you envision the future to be like. It seems to some degree you've lost hope that secure system design
I wouldn't be that extreme in dismissing the promise of more secure system design. Nevertheless, I feel that a determined adversary, a well-funded adversary, will always get through. And therefore, we must have the means of resilience. And to me, this kind of a agent that is residing on the system, being prepared for the fact that it will be penetrated, and will be prepared to take some actions that will enable the system to continue to operate at least at some degree of effectiveness. So that's the thrust of what I'm talking about. I do not dismiss the important work that's being done in secure system design. Yes, sir.
So I'm noticing a lot of the constraints on our models, so like limited amount of reads, also apply to any sort of like adversarial models that might, be attempted to train. Are you aware of any research that actually of adversarial training in that context?
Adversarial training?
Or just like sort of like are you aware of like are you interested in or researching sort of the idea of adversarial training with the same constraints that like are?
Yes. So yeah, essentially training on whatever observations we have about the adversary. Maybe that's what you're talking about. All we know about the adversary is what we can observe about the adversary. We have some observations about our own systems, about some attributes of the adversary over time, and the actions of the adversary over the time. That's the complete set of data that we would normally have in principle. And that's what we have to learn from. Now, this model can be enriched by assumptions about how the adversary might work. We might do some symmetrical assumptions. For example, we execute such and such attack in such and such manner. Maybe we can assume that they will do something similar, right? So we can enrich that model by those priors.
We have time for one more question.
Thanks for the talk. I just had a question around explainable AI. Are you seeing that becoming more of a trend, common requirement from people?
Could you repeat this again?
Explainable AI.
Oh, explainable.
Is that something you're getting more, it's becoming more of a requirement to deliver when you produce a solution?
So, I believe DARPA Explainable AI program is an amazing program. It's run by Dave Gunning, who has an amazing record of producing highly successful results. He was my colleague at DARPA at the same time when I was there. He was there. It is going to succeed to some degree. However, I think explainable is a very high bar. Humans don't do very well in explaining themselves to other humans. Why do we expect AI to be able to explain itself to humans? However, what we can and should, and I think what Dave Gunning really is shooting for, is to come up with techniques for the AI systems to present information about what they're doing and what they're thinking in a way that is a little more digestible by the human beings, and so that they could make some inferences about what they're doing. And so in some ways, any explainability is not about to actually explaining it, it's about presenting some information that we can infer explanation from, right? So hopefully that is doable. We actually do some research in that. In other words, how to represent data to the humans from the AI system in a way that makes it easier for the human to understand what is it that they're doing without an explicit explanation. No explicit explanation, merely a representation that helps the human to create explanation, which could be wrong. But even wrong things are often helpful. All models are wrong, some are helpful. Thank you.
Thank you very much. Please join me in thanking Dr. Kott one more time.